My name is Oliver Slattery, and I work at the NIST Gaithersburg, Maryland, and I will be the chair for the first session of this afternoon. The format will be one invited talk and three contributed talks. And so we will begin now with the first invited talk, entitled Fundamental Limits of Repeaterless Quantum Communications, and it will be presented by Stefano Pirandola.
Okay, thanks a lot. Okay, so it's a very pleasure to be here to QCrypt 2016. I just have my coffee, try to be awake during my talk. So this is a joint work with other people at the University of York, in particular Riccardo Laurenza, Carlo Ottaviani, and also an external collaborator from the University, from the UCL, University College of London, Leonardo Banchi. So this is the paper that you may find on the archive. We can call that a PLOB paper, just by our initial. Don't try to find the meaning of PLOB on the internet, because you may find very strange words, strange synonyms. But here we go. So let's give the outline of the talk. So I will start with motivations. So why we have basically tried to achieve what we have done, basically. And then I will talk about some definitions. You've already seen some of these in the previous talk by Mark Wilde about adaptive quantum protocols. And then how you may define two-way assisted capacity, okay, for quantum and private communications. Now, most of the talk will be actually on methodology, so how to compute these capacities, so how to find upper and lower bounds. And then at the end, I will talk about specific application of this methodology, so the formulas that we found for Gaussian channels and discrete variable channels. But let's start with the motivation. So this is a very strange, number, very strange code, but it has a specific meaning. So it is more or less the current standard of IEEE for classical data transmission in a Ethernet network via optical fibers. And what you see is basically that we have a number here which is 100 gigabits per second. So classical infrastructure is very fast, okay? So we really are using high-speed connections, okay? We have comparable numbers, okay, for other types of network, of course. So this gives us basically a message that if we want to compete with the classical infrastructure, we need to achieve high rates. So not just distance, but high rates for our quantum and private communications. So ideally, one would like to have high-speed protocols for all these tasks, okay? Quantum communication, and by that I mean the transmission, error-free transmission of qubits, entanglement distribution, so the distribution of A bits, okay, between entanglement bits, okay, between two remote locations, and of course QKD, okay, so the generation of secret keys between remote parties. Okay, so we have this open problem, okay? We have Alice and Bob connected by a channel, okay? And we want to determine what are the maximum rates, okay, for all these tasks, okay, for quantum communication, entanglement distribution, QKD, that they may achieve, okay, in absence of quantum repeaters and without any pre-share entanglement, okay? So that's a point-to-point connection, okay, simply as that. And we want to optimize these strategies in order to maximize the rate of the communication between these two parties. Now, the most general strategies that we may think is based on local operations and unlimited two-way classical communication. So what we mean? We mean that Alice, okay, prepares some input to the channel with some local operation. Bob makes some measurement, usually, and then there is a two-way communication. So there's a feedback back to Alice, and some forward communication to Bob in such a way that they optimize their local operations. So it's an iterative process that can basically go on in each use of the channel. So this is what I mean by adaptive LOCCs. So adaptive to local operation and classical communication. Okay, this kind of the most general process, the most general classical strategy that you may think at the end of the at the ends of the channel. Okay, optimizing over this kind of LOCCs, then you define the two-way capacity of the channel. Okay, so it's really the top that you may achieve in terms of rate. Now this is difficult because of the feedback. Okay, so that's a very difficult problem because of this real-time feedback that you may have. But likely, we have basically computed many of these two-way capacities after more or less 20 years, let's say maybe 17. The first two-way capacity was computed in 97. That's 19 years. Okay, so adaptive protocol, let's go into more detail. So there are not too many formulas in my talk. More or less, they are all like pictures like this. So we're talking about this kind of situation. So they have Alice and Bob. Okay, they are separated. They have to achieve some arbitrary task. It can be one of the three tasks I just talked about before. And they can use a system in arbitrary dimensions. So qubits, qubit, bosonic systems, and there is no restriction, okay, in this particular description. So first of all, they have local registers, A and B. So you may think like quantum systems they can access, okay? They can be countable, so whatever they want, okay? We don't want to give them restrictions locally, okay? So they have this countable, they have these countable ensembles of quantum systems locally. Then, okay, they apply a first preparation LOCC, okay, to prepare basically the input to the channel. There is the first transmission to the channel, so Alice picks a system which is sent through the channel, and Bob gets an output, okay? Then there is another LOCC, okay, among basically all the register systems, of course also involving the output. That is the second system picked by Alice, sent through the channel, another output, another LOCC, and so on. So basically it's like transmissions and between two LOCCs, okay?
The channel is unidirectional.
Sorry?
The quantum channel is only one direction.
I mean, this particular example is one direction, but it doesn't have to be. Okay. Okay. So, so we have basically many adaptive LOCC and rounds. Okay. So we have that these LOCCs. Okay. You think that we are starting from some fundamental state. Okay, for the registers. So what you have a sequence of LOCC defining a protocol. Okay. And also, of course, you have an output. So the output state of the registers, and you want that output is close, okay, in trace norm, okay, epsilon close to some target state, having basically n-r bits. Now, what is this target state? It depends on the task of the protocol. I will discuss this in a few seconds. So what happens is that if that's the target state with this number of bits, then okay, we say that that protocol achieved that rate. Okay, this of course we are not giving all the mathematical details of the epsilon, but just the main idea here. Okay. So okay, so that's an adaptive protocol with some rate. We want to optimize this. So first of all, we want to consider asymptotic rates. So many uses of the channel. And also, we would like to optimize over all the adaptive protocols, okay? So over all the possible strategies. And in this way, we can define the two-way assisted capacity, okay, of the channel. I say generic because it depends on the task, again. In particular, suppose that the target state is a maximum entangled state, so you want basically distribute A bits, okay? So we are talking about here, so that capacity is a two-way entanglement distribution capacity, okay? So basically it's the maximum number of A bits you may transmit through the channel, okay, per use of the channel. But also, this is equal to the two-way quantum capacity of the channel, because in this particular setting with two-way classical communication, it's completely equivalent. So basically, if you're able to distribute an A bit, you may teleport a qubit. Okay? If you're able to transmit a qubit reliably, then you can send part of an A bit. So this basically one-to-one correspondence between these two quantities. So that's the maximum number of qubits, okay, that you may send through the channel per use of the channel. But then we also consider a different target, the private state, okay, as introduced in this paper. So basically, the private state is a sort of generalization of maximum entangled state, if you want, and contains some number of secret bits, okay? And this defines the secret key capacity of the channel, okay? So basically, doing this optimization, if the target is a private state, gives you the secret key capacity of the channel, or the private capacity of the channel. And that's higher than the entanglement distribution capacity, just because a secret bit is more general than an A-bits, okay? So an A-bits, if you want, is a particular type of a secret bit. So, okay, so here we are. You see, these are the definitions. We have this situation here. So we have these capacities, two-way assisted capacity, with these general relations. Now, how we compute them? So first of all, we need a lower bound. So from one point of view, lower bound is easy because we just need to specify some entanglement distribution strategy, okay? We want a lower bound for this quantity here. So you may think that Alice and Bob implement a particular protocol, okay? And this particular protocol could be just Alice sending part of EPR state through the channel, okay? So she keeps one part and sends the other part to the channel. This defines, okay, at the output, there is Bob. So this operation defines the Choi matrix of the channel, okay? So after this transmission, Alice and Bob, they have the Choi matrix of the channel. So Alice does that many times. They collect a number of Choi matrices, okay, and they apply one-way distillation on this collection, okay? Now this defines the basically one-way entanglement distillation rate of the Choi matrix of the channel. And that's basically is a lower bound for that capacity, okay? Now, okay, this might be a complicated name, but important is that this is computable, or better, or more exactly, we can compute another lower bound, because using an equality called hashing inequality, proved by Dephasing and Winter, we have that this rate is lower bounded by these two quantities. Now, these are basically the coherent formation and the reverse coherent formation of the Choi matrix. So you have this state, the Choi matrix, you compute the coherent formation, you compute the reverse coherent formation of that, and this gives you the maximum, it's a lower bound for that. And you can compute this, because it's just computing for Neumann entropies on a state, okay? So that's good. So we have a lower bound. Now we need an upper bound. This is a bit more difficult. In fact, we only achieved that recently. Now, what we do, we combine several ingredients. Okay, first of all, relative entropy of entanglement. Okay, what is that? It's a sort of, relative entropy of entanglement is given by this definition. It's basically, you have a state, you compute the relative entropy of that state with respect to a separable state, sigma, okay? And then you minimize over all the possible separable states. And you get the relative entropy of entanglement of the original row. So if you think something like that, you have basically, it's a sort of distance, if you want, of the state row from the set of a separable state. Of course, if a row is separable, this quantity is 0, okay? But if the maximal entangled, the distance is the maximum, okay? So that is the one possible measure of entanglement. Then we have another result that we can use. The distillable key of a state is bounded by its relative entropy entanglement. So this provides a good upper bound for the distillable key of a state. Now, what is a distillable key of a state? I have a state that takes n copies of the state. So Alice Bob, they have basically n copies of this. They apply a protocol, okay, to distill secret bits, okay, similar to what happens with entanglement distillation. And the maximum that you use, that may achieve per copy, is given by that quantity here. Okay, that satisfies the upper bound. And then we have another result, which is basically a sort of continuity for relative entanglement. So if you have two states which are epsilon close, their relative entanglement, they are sufficiently close. Okay, so you put everything together, all these ingredients together, and you find an upper bound. So we want something here, remember? Okay, so we found an upper bound in terms of the relative entanglement. it's a sort of extension of the radio entanglement from states to channel. Okay? In fact, this quantity depends only on the channel. Okay? So it's similar to that bound, but not for states, okay, but for channels, okay, for any channel. And it's a bit difficult quantity because it still has some adaptive here description. In fact, you see that this is given by, that's the output of the protocol. It's very complicated because it's an adaptive protocol. You have to compute the radio entropy of, that output over the n, which is the uses of the channel, take the limit, take the supremum over all the possible protocols. So it's actually difficult, okay? So this is difficult. It's an upper bound, okay, but too difficult. So what we can do? So we have to deal with this quantity, okay? What we can do, we can simplify the output state, okay? So we want to find a simplification of the output state, so some sort of representation of the output state of the registers in such a way that we can simplify this quantity, or find, more exactly, an upper bound, which is easy to compute. So this basically, we design a teleportation-based a technique for doing this, which is based on previous results. Okay, I'm going to show you now. So this is teleportation stretching. So basically, it has three ingredients. First of all, a teleportation simulation of quantum channels. Okay, this is a very, very important tool. And after that, there are some manipulations that we're going to do on the Choi matrices and on the adaptive LOCCs of the protocols that allows you to reduce basically the adaptive protocol into a sort of a simpler block protocol, okay? Achieving the same task and the same output. So this is basically, there was previous intuition, but exactly this kind of goal is very general, and I didn't find that we didn't find this in previous literature, despite there are, of course, many previous insights, okay, regarding teleportation. But let me show you more exactly on these points, more precisely, okay? First of all, that point, which is very important. Okay, so this was an argument. So basically, the first step here, it was an argument first introduced in '96, okay, in this paper. So to explain this, start from the standard teleportation protocol, so infinite dimension. So what happens in a standard teleportation protocol, you have Alice and Bob, okay, they share a Bell pair, or a Bell state, okay, called here pure state, okay, of system A and B, so qubit A and qubit B if you want. And then, so it's a maximum entangled state. The Alice as an input system, she applies a Bell detection on these two systems. There's an output K, okay, which are just 4 numbers for qubits, and this is communicated to Bob. Okay, Bob applies some corrections, which are basically Pauli operators, okay, depending on K, and receive the output system B. Okay, so okay, this is of course a very, very famous protocol. What happens? You have a sort of a transfer operator, if you want, an identity map from system A to system B. So you may basically teleport the state from here to here. Okay, so it's an identity channel if you want. Now, what happens if we change that state? Okay, we don't consider a maximum entangled state, but a general mixed state. Okay, if you consider a general mixed state here of these two systems, sorry. Now you don't have, a perfect teleportation. Okay, you have teleportation with some noise. Now the idea is that this noise simulates a channel. Okay, so you don't have here a rho, but you have the output, which is at some channel applied to rho. I'm just finishing my. Okay, so that's the idea. So you have a teleportation channel, okay? So a channel simulated by teleportation. So the problem is that, okay, what channels can be simulated? Okay, so that's the next question. Using Bell detection and standard Pauli corrections, okay? So you can simulate all Pauli channels, okay? That was shown by Bowen and Bose in 2001, okay? So it's a wide class, okay? But of course, they are not all the possible discrete variable channels, okay? But it's a wide class. So very good, nice idea, okay, seminal paper. So what we want to do. We want to generalize this, okay, not only us, but I'll show you other paper too, to generalize this idea, okay? So what we want to do, we want, first of all, to generalize the resource state. So we allow for different dimensions, okay, between A prime and B prime, okay, even discrete variables, and also possibly consider continuous variables, so infinite dimension, okay? And of course, because of this modification, you also need to consider more general corrections here, okay, not just Pauli corrections. So if you do these modifications, then you can simulate many more discrete variable channels. You may simulate also continuous variable channels, and even hybrid channel between discrete variable and continuous variables. So you can really you can really have a much wider class. Okay, so how do so let's try to define this class, okay, in general, and then explain why it's possible, why it's so big. So the most general class of channels that can be simulated by generalized teleportation in arbitrary dimension is sort of, we call that teleportation covariant channels. Okay, use stretchable because they are those channels that then can be used in this stretching technique, okay, afterwards. But teleportation covariant really gives you the idea of what's going on. So basically, this channel, channel epsilon, is teleportation covariant or stretchable if happens this situation here. So basically, if it is covariant, okay, with the teleportation unitaries. So basically what happens is that when you perform a teleportation, you don't teleport perfectly the state, but you have a Pauli unitary or a displacement, if you're a continuous variable, to correct. So this is the unitary which is here, okay? Now what happens is that you don't correct the state, but you consider the output of the channel, okay? You have this state. Now, a channel is stretchable teleportation covariant when you can push that unitary out of the channel, okay? This doesn't need to be the input unitary, and even shouldn't be, in general, it can also be in a different group, okay? So you have, I don't know, here the Pauli group, and this could be some different group, okay? Some different representation, unitary representation of the group. So, but this is the property, okay? And because of that, you can simulate Pauli channels. So this class, the class of channels satisfying this property includes Pauli channel, Erasure channel, bosonic Gaussian channels, and so on. But let's describe what happens more exactly, okay? So this is the direct transmission, okay, through, say, a stretchable channel with that property. Already 18 minutes here. Really 10? Wow. But it was the guy that just took my first 2 minutes before. Yeah. Okay. Okay, so very quickly. So what happens is that you insert teleportation here. So you don't transmit, you use teleportation. So there's an EPR pair here. And this bell detected now. It's not sent to the channel. So basically you teleport from here to here, up to a random unitary. What happens, okay, then this is the output of the channel, but now since it is stretchable, okay, you can write the output like this, and now you can invert the unitary, okay? So you can correct the output here, and you got exactly the channel. So you can do the correction at the output system, okay? So then see that basically what I've done here, I just defined the Choi matrix of the channel, okay? So at the end of the day, everything is somehow simulated by the teleportation of the input system, A, on considering the Choi matrix of the channel as a resource state. So basically what I'm saying is that that transmission can be simulated by teleporting, okay, over the Choi matrix of the state. So that's basically the idea. Now, since I have not so much time, I just want to tell you that the same procedure can be done with continuous variables, okay? You just have basically some imperfect simulation when you use imperfect sources and imperfect measurement. but then you can take simply the input, a limit on the, sorry, as an input, a limit on the output, and you exactly retrieve asymptotically the description of the channel, okay? Of course, I mean, as I told you before, this is basically an argument that's been developed through time. So there are many important contributions, okay? So starting from the 96 paper, the continuous value teleportation, Werner's paper on generalized teleportation protocols, the first extension of this telesimulation by these protocols, by these, papers, and then, okay, our result. Okay, by the way, let's see what happens now. So that was the first step, okay? So so that's the first step. Then we see the second and third step very quickly. So that's the adaptive protocol, transmission between two LOCC. First step, you replace the transmission by teleportation over the Choi matrices. That's, okay? So you simulate the channel with teleportation, introducing the Choi matrix. That's the first step. Okay, the second step, now, since this is a state, you can just somehow stretch out of the logs the state. So basically, you're anticipating in time the Choi matrix, okay? And what you get is that you have the Choi matrix here with some local operations and classical communications afterwards. You may iterate this for all the transmissions. At the end, you have a bunch of Choi matrices, okay, and a tensor product of Choi matrices. And these are processed by basically a single but very complicated trace-preserving LOCC, which somehow includes all the adaptive logs of the protocol. So at the end of the day, with these three steps, okay, you have that the output state is decomposed into Choi matrices up to an LOCC. Okay, so that's the central result. So we have achieved the decomposition of the output state, which is very useful. Okay, and now I'll show you what this can be used. How we can use this. Okay, so let me just go to the final step. Okay, so we combine the ingredients. So remember, this was the upper bound. But very difficult because of that state. Now we apply this technique, teleportation stretching, and we can decompose into this way. Okay. So we combine the two things. What we do now, we compute the relative entropy entanglement, the quantity, using this decomposition. Now we use very important properties of the relative entropy entanglement, which is monotonicity under LOCC, and then subadditivity over tensor products. So you see, we started from this, and we got that. So it means that we have now n times the relative entropy entanglement of the Choi matrix of the channel. So this is a single letter quantity, okay? So we are done, because, okay, now we replace there, okay, right? So we got another upper bound here, but you see that we can simplify and we can simplify the supremum. So what happens is that we get rid of the number of the uses, but also of the adaptive logs, because they just disappeared, okay, in that trace-preserving global log that we introduced. So what we get at the end, that upper bound, okay? So the two-way capacity of a stretchable channel is bounded by the relative entropy entanglement of its Choi matrix. And we can compute that now. Okay, we have other considerations that I'm going to skip. So what we get at the end is like this, okay? So the two-way capacities, lower bound and upper bound. So I just call that quantity in this way, okay? I call that entanglement flux of the channel, but basically that's exactly that quantity there, okay? So we have this lower bound and upper bound. Okay, this applies to all stretchable channels, so Gaussian channels, Pauli channels. In particular, there are some of them for which the two bounds coincides. Okay, so you have the lower bound is equal to the upper bound, and for these channels, we can compute exactly the two-way assisted capacity. Okay, so that's basically the deal, and we are lucky because this coincidence, okay, is very common, I mean, to many channels, and so we can compute the two-way capacities of all these channels here. Okay? And now this is basically the end of the methodology, and I'm going to show you very quickly the results for these channels here. So the lossy channel, okay, with transmissivity eta. So that's the two-way capacities. So we know a lower bound from 2009, okay? And we computed the upper bound, okay, they coincide, very lucky. So we can say that for a lossy channel, so a B-splitter with transmissivity eta, okay, we have that all the two-way capacities here coincide, and they are equal to just this simple formula here, okay, minus log 1 minus eta, okay? So all this also coincide with the maximum discord, okay, and most importantly, so this gives you a rate loss scaling. So we found that for low transmissivities, this behaves in this way. So basically, the maximum that you can get in, for instance, a QKD protocol, okay, is 1.44 eta bits per use, where eta is transmissivity of your optical fiber. Okay? And this improves the previous result by Takeoka, Gu, and Wilde. So we have that situation there, where this is basically the CKK capacity, okay, of the lossy channel, plot in terms of the distance, and this is basically bits per use. And, okay, that is the previous bound, the TGV bound, and these are basically the protocols that we have now. Okay, so continuous variable protocols, the purple lines, but also discrete variable protocols, the dashed line. So you can have an idea of how far we are from the ultimate limit. What? Finish? 1 minute, 2 minutes? Okay. Right. Then we have so that's important because this gives you really the fundamental rate loss scaling for QKD, for instance. Okay. In this case, in this particular case. Okay, thermal loss channel. We found the two-way capacities also for quantum leading amplifiers. So if you consider like an amplifier with gain G, okay, this is also distillable. And you may find the two-way capacities which are coincident and have this simple formula here in terms of the gain. Then, okay, this is not, and then, okay, result for discrete variable channel. So if you have the phasing channel like this, so qubit dephasing channel, your block sphere is basically squeezed in one direction in this way with some probability P, okay? So what you get is that it's distillable, and the two-way capacities are a simple function of the probability of the phasing, okay? Then we have the phasing, okay, this can be generalized to qubits, okay? So the formula just a little bit different. We have the dimension here and the channel entropy here for the area alphabets. And then you have, okay, the ratio channels too. With some probability P, you have no output, so you have basically an erasure output. With some probability 1 minus P, you transmit perfectly the state. And then this is also distillable. So, and the two-way capacities are equal to 1 minus P. Actually, this was, okay, and then we have the dimension, the formulas. So this was the only thing that was known before in 97, okay, the two-way capacity of the erasure channel. So actually what the new thing is the CKK capacity, okay, that has been proven in this paper, and also independently by Good and out in this other archive submission that I think is now published, I guess. Okay, so the Dephasing channel, we don't know if it's distillable, and we only have lower bound, upper bound, and so on. So, conclusions. Most of the talk was about the methodology. So we tried to, in the paper, we somehow design a method for computing two-way capacities, combining relative entropy entanglement for channels and teleportation, okay? And this allows us to find many two-way capacities, okay, for many channels, for both continuous variables and discrete variables. Now, these are important because these are the maximum rates in point-to-point communication. So they also represent the benchmarks for quantum repeaters. Okay, so if your quantum repeater works, it can outperform the maximum point-to-point rate, okay, given by these two-way capacities. Now, there are also some other developments. This is the last slide. Mark before talked about the strong converse rates. So one can basically extend the results to finite n uses of the channels. And we also, there's also an extension for broadcast channels in these two papers here. Recently we also applied the methodology to quantum metrology. Okay, so to simplify adaptive protocols of quantum metrology and quantum channel discrimination. And also there's a paper extending the results to the presence of repeaters in a quantum network. So basically, what is the maximum rates that you may achieve with a single repeater, with two repeaters, and so on. Open problems, of course, there are many capacities which are for which the two-way capacity, many channels for which the two-way capacity are not known. In particular, the thermal loss channel is very important. And also the polarizing Rampio damping channels, we don't know their two-way capacity. So this is basically a matter of current investigation.
Thank you, Stefano. So we have time for a couple of quick questions. Questions? Yes.
Jenny.
At the beginning of your talk, in the motivation, you mentioned 100 gigabits rates for the classical communications. And you said that your work is to find some bounds on quantum communications to see whether we can achieve these rates.
Yeah.
Do you have an answer now? Can we achieve this?
Yeah, let me tell you that the main message in this, for instance, in this plot here, is this the maximum you can get per use of the channel. Now, that's not per second. So it's per use of the channel. So to have per second, okay, you have to add this result, and then you have to plug a clock. So for instance, this can be used to understand, okay, if I use some clock, okay, what is the maximum I can achieve? If I use another clock, what is the maximum? Because I mean, these bounds are universal. I mean, okay. So it can give you this information. So maybe we can achieve the same 100 gigabits per second with one of these protocols, okay, maybe continuous variables, and with some clock, okay, and we know more or less what is the clock that we have to develop, okay, for this goal. But of course, we are not close to 100 gigabits per second. We are very far from that now. Yeah.
Okay. No questions? Okay, well, let's thank the speaker again.
Okay, thanks a lot.